very much. And thank you for the invitation to come to Merced. Prior to the invitation, I didn't know the city of Merced existed, let alone the university. Now I know about both, and I have been really impressed by seeing the exciting things that's happening here. And I think you guys are in a unique position, starting something from scratch to really build something unique and great. So I'm glad to be a small part of it. Okay, as Stephanie has said, I work on phonological variation, and today I'm going to talk about that aspect of my research. And I'm going to take a higher level approach to it. I'm kind of trying to give a flyover view of the research program that I've been working on for the past decade or so. So rather than focus in detail on a few specific variable phenomena, I'm going to talk about what I think the architecture of the model should be to account for the types of variable phenomena that we observe in phonology. So I will talk about a few specific examples, but I'll get less into the data and more into the kind of big picture type questions. And to begin that, I'm going to start by talking about the ways in which phonological variation has been handled in phonological grammar, theoretical phonology, over the past 5 or 6 decades. And obviously, when one tries to squeeze 5 decades into 5 minutes, it is going to contain quite a bit of overgeneralization. So part of what I will say here is true of the field in general, but certainly not true about specific individual ways in which things have been modeled. So the first slide here is an attempt to show how phonological variation was viewed in the very early years of the generative tradition. So during these early years, the idea was that grammar is a function. So it took a single input and generated a single grammatical output for that single input. So it was a one-to-one mapping between input and output. So, an input going through the grammar giving us one single grammatical output. However, even in these early years, there was recognition that actually observed speech, things that left people's mouths, was full of variation. So there was acknowledgement that variation happens, but the idea was that variation didn't originate in the grammar, but in the implementation. So the grammar would put out a single invariant form. That form has to be physiologically realized and instantiated acoustically, and it's in that implementation process that variation could have been introduced. So variation, to the extent it was acknowledged, was mostly considered as something outside the domain of linguistic theory, something that grammar didn't have to deal with. Now, this is a generalization. There was very early phonologists who acknowledged that grammar itself has to be variable. In fact, even Chomsky and Halley and some pattern of English had some variable rules. So there was some acknowledgement for variation from the grammar, but it was mostly relegated to post-grammar processing and not coming from the grammar itself. Roughly at the same time, well, more than roughly at the same time, actually at the same time as the development of early generative approaches to phonology, so Chomsky and Halley's sound pattern of English, Lebov developed the variable rule approach to phonological grammar. And one of the core principles of the Lebovian approach was that grammar itself is variable, right? So we got variation from grammar itself. We would get an input into the grammatical model, and the grammatical model can generate more than one grammatical output. Another hallmark of this Lebovian-inspired variable approach to phonology was that it wasn't only grammar that determined variation, but a whole host of factors co-determined the actually observed patterns of variation in speech. And there was no formal distinction made between the contribution of grammar and the contribution of all the various social factors that they looked at. They were sociolinguists after all. And also, many non-social factors, kind of like speech register or usage frequency. They were all acknowledged as contributing towards variation, and the way that they were implemented in the model, no formal distinction was made between these different sources of variation. In the early 1990s, we had a big shift happening in phonological theory as the theoretical models moved from more rule-based models to more constraint-based models. So the introduction of optimality theory and related models of phonological modeling. And in those models, variation became much more central to the main core of generative approaches to phonology. In fact, many models were developed within that constraint-based framework that were developed specifically to account for variation. And we're now at a place in theoretical phonology where the sufficiency of any model that you propose of phonological grammar is measured at least partially in terms of what it can account for variable phenomena. So now it's part of the core set of data about which even generative theoretical phonologists care. So all these models that were developed within that framework since the 1990s acknowledge that grammar itself contributes to the observed patterns of variation. So grammar is no longer a function, it can map one input grammatically onto more than one output. What is also true about all of, or most of these models that have been developed since the 1990s is that unlike the Lebovian model, which assumed that grammar and non-grammatical factors co-determine the patterns of observed variation, these models are, at least in their practical implementation, purely grammatical models. So they make no formal allowance for factors other than grammar to determine the patterns of observed variation. For some of the people working in that framework, this was not a statement of principle, but just a statement of expediency. Say, let us first develop models that only account for the role of grammar, acknowledging that other factors might also contribute, but simplifying by ignoring the other factors and therefore not making a formal place in the model for these other factors. For some authors in that tradition, this was a statement of principle, saying that no, actually, grammar is the thing that determines the observed patterns of variation. So within this broad background, I'm going to propose a fourth kind of hybrid model of how the architecture of this system works that is responsible for generating the observed variation in phonology that we see. And in this model, I'm going to assume that grammar itself is variable. So this follows kind of in the Lebovian approach and in the more recent constraint-based approaches to phonological variation. And the idea is going to be that grammar is responsible for determining the space of possible phonological variation. So grammar is going to tell us for this input, these are the grammatically allowed variants that should be observed. And then along comes the non-grammatical factors, and what they do is they can just shift us around within this grammar-defined space of possible variation. So the non-grammatical factors are subservient to grammar. They can't introduce new variants that the grammar didn't allow. They can't eliminate variants that grammar allowed. They can just say within the set of grammar allowed variants, how frequently am I going to observe which of these? Right? So it's a grammar dominant model. And in that sense, it's different from the Lebovian approaches where there was no formal distinction between how grammar contributes to variation and all these non-grammatical factors contribute to variation. This is a model in which grammar sets strict limits of what we should observe, and the non-grammatical factors just play a role in the actual implementation of speech. It's also different from, say, the models that have been more prominent since the 1990s in the constraint-based theories of grammar. So they kind of stopped at this point, right? Now I'm adding in the second level, saying now these non-grammatical factors is going to come and kind of interpret the variable output that grammar produces. So what I'm going to present today is a mathematical implementation of this type of model and then apply it to a couple of sets of variable data to see how well this model actually fares at explaining the observed variation that we see in speech. So this is an abstract representation of the mind of the speaker or listener. Everything inside of the blue line is kind of the mind of the speaker or listener. And the idea is that, grammar contributes to what the speaker is going to do as a speaker or the listener as a listener. If we think about it from the perspective of the speaker, grammar is going to determine what commands we're going to send to the motor cortex, which is going to move the speech organs, which is then going to output some kind of acoustic output outside the head of the speaker, and we can flip it around and look at it from the perspective of the listener. So the listener will get some acoustic input, through the ears, and then we'll have to interpret that acoustics, and grammar is part of what's going to determine how to interpret the acoustic cues. But what I will try to argue for is that it's not only grammar, there's a whole host of things that co-determine with grammar what the observed patterns of production is and how to interpret the variable acoustic input that we get. And I think what we really need to do is no longer just try to model the role of grammar, but try to model what happens inside of that black box. So this kind of executive function that puts together all these various factors that contribute, figure out how does that function work? How do we relate all these various factors with each other? How do we weigh them relative to each other? I'm going to look at 3 sets of data to illustrate that. We will start out by looking at TD deletion in English, variable TD deletion. And here we're going to look at how grammar interacts with usage frequency, and we will look at this from the perspective of the speaker. Then we will look at variable crossword nasal place assimilation in English. We will look at this from the perspective of the listener, and we will look at how grammar interacts with speech rate. And lastly, we'll look at variable realization of voicing in Afrikaans, and there we will look how grammar interacts with the role that a person have in an interactive context, whether you are the listener or the speaker, and how you're going to use the grammar differently based on which one of these 2 roles that you play in the interactive situation. So the challenge that we have is, if we want to develop an adequate model of phonological variation, this model should have the following properties. It should be a model in which grammar itself is variable. There are decades of evidence amassed now showing that grammar isn't an invariant function. Grammar itself can produce variation. It should also allow non-grammatical factors to contribute, because there's just as much, if not more, evidence showing that non-grammatical factors co-determine patterns of observed variation. But kind of most importantly, it has to be a model that has very explicit integration principles for how we're going to integrate the contributions of grammar and non-grammatical factors. So we need this kind of executive function and that's maybe in a cognitive science setting the wrong word to use, because you might have a different connotation with executive function. For me, it's just whatever happens in the black box, right? Something that takes input from various factors and balance them relative to each other. We need a model for that. So the model that I'm going to develop is developed inside of harmonic grammar. So this is a constraint-based model of phonology, of grammar. And that is basically a mathematical summary of classic noisy harmonic grammar. So the way that it works is, I have an input that goes into the system. A whole host of candidate pronunciations are generated, and each one of those candidate pronunciations are evaluated by a set of weighted constraints. And they're assigned a harmony score for which you have the formula there. It's basically calculating, well, not basically, it's exactly calculating a weighted sum of constraint violations, right? So every candidate gets a harmony score based on how many times it violates each of the constraints and the weights of those constraints. And then we can compare these harmony scores with each other, and the observed output will be the one with the highest harmony score. This is noisy harmonic grammar, and the noisy part is relevant. That is where we get variation from. So every time we use the grammar, the weight of every constraint is perturbed by a small random amount of noise, positive or negative. And the effect of that is that the harmony score that an individual candidate will be assigned will never be the same from one time using the grammar to the next time, because the weight of the constraint will be perturbed by this noisy component of evaluation. And that's how we get variation, why the noisy variation in the constraint weights. The harmony scores of candidates will also sometimes vary, and sometimes one candidate will have the higher harmony score and sometimes another one. So the noisiness is important. That's where variation comes from. This is classic noisy harmonic grammar. It is a purely grammatical model of variation. There's no place in that model for non-grammatical factors to contribute. The constraints which we have there are purely grammatical constraints. So we need to find a place for the non-grammatical factors inside of that formalism. The first step to get there is to divide the constraints into 2 sets, or not necessarily the only way, the way in which I'm doing it here today. Let's divide the set into 2 sets of constraints, the markedness and the faithfulness constraints. So markedness constraints, constraints against having specific structures, and faithfulness constraints, constraints against changing the input somehow. So this is still mathematically equivalent to the first one. We just took the set of constraints and split it into 2 sets. To get the non-grammatical factors in there, I make yet a third addition, a third change, and that is by adding a scaling factor into the faithfulness constraint evaluation. So the scaling factor is where the non-grammatical factors come into the system. So now every time the grammar is being used, the markedness constraints are just perturbed by noise. The faithfulness constraints are still going to be perturbed by noise, But there will also be this scaling factor, which will be how the non-grammatical factors will move the faithfulness constraints up or down during evaluation. So they can cause faithfulness to contribute more towards the calculation of the harmony score or less by moving the faithfulness constraints up or down. So now we have a formal mathematical system that allows for both grammar, we have constraints, and non-grammatical factors, the scaling factor, to contribute to the harmony score. And I'll go through a couple of examples in the rest of my presentation showing how this can be applied to different variable phenomena and see how well or not does it succeed at accounting for the data. Okay, so let's get to the first example of implementing this model. And here I'm going to talk about variable word final TD deletion in English. So this is based on research that I have done together with a friend and colleague, Shigeru Kawahara, who is now at Keio University. When we did the research, he was still at Rutgers University. So TD deletion is this phenomenon in English whereby words that end on consonant clusters, the final segment of which is a T or a D, can be pronounced with or without that final T or D grammatically. So a phrase like West Bank can be grammatically pronounced in English as West Bank with the T or West Bank without the T, right? So it's a variable phenomenon. They're both grammatically acceptable in English. It is a very extensively studied variable phenomenon in the Lebovian sociolinguistic literature. It has been studied for literally hundreds of different varieties of English and also for Dutch and German. So we have a very good understanding of what all the factors are that contribute towards determining at a given moment of speaking whether or not you're going to delete this final T or D, both grammatical and non-grammatical. So I'm only going to look at one grammatical and one non-grammatical factor as examples of the things that contribute towards determining deletion rates of these T's or D's. For a grammatical factor, I'm going to look at the following phonological context. So here you have data from 8 varieties of English showing deletion rates in 3 phonologically defined contexts in these different varieties of English. So if you look at the table, in all of these varieties, deletion is observed most frequently in preconsonantal context. So in a phrase like West Bank, where the following word starts on a consonant. This has been observed in every single variety of English for which this phenomenon has been studied, and in those varieties of Dutch and German for which it has been studied. So that seems to be a very strong generalization, most deletion before a consonant. Then the varieties of English and also of the other languages split into 2 groups. Some show more deletion before a pause, so in kind of utterance final position. So these first 5 varieties of English are examples where there's more deletion in pre-pausal than pre-vocalic context, and some show more deletion before a vowel than before a consonant. Okay, but this is just a typical example of a phonological conditioning factor, right? Whether something stands before a consonant, a vowel, or a phrase boundary is very typical of the conditioning factors you would find in phonological rules, even categorical non-variable phonological rules. So clearly, grammar is one of the things that is going to play a role in determining how often you're going to delete. We're going to focus particularly on this last one. This is English as spoken in Columbus, Ohio. These data come from the Buckeye corpus. It's a corpus of sociolinguistic interviews with 40 lifelong residents of Columbus, Ohio. An interview of at least an hour with each one of these speakers that has been fully phonetically transcribed. It's a great resource if you want to get data from kind of English in the wild variable phenomena. So those numbers we just extracted from the Buckeye corpus. So this is the grammatical factor that we're going to be looking at for TD deletion. For a non-grammatical factor, I've chosen usage frequency. So we know for many different variable phenomena, and typically these are reductive phenomena, so things like deletion, intervocalic voicing, so lenition processes, that such processes are more likely to apply to words of higher usage frequency rather than words of lower usage frequency. So even 2 words that are phonologically equivalent might be affected differently by this TD deletion process based on frequency. 2 words that are phonologically equivalent, if one is higher in usage frequency than the other, we will see more TD deletion in the higher rather than the lower frequency word. So this is again showing you the data from the Buckeye corpus. Let me just orient you. Here's our 3 phonologically confined contexts, right? Pre-consonantal, pre-vocalic, and pre-pausal. On this axis, you see the deletion rate. And on the x-axis, we have the frequency of these words as calculated in the SELEX corpus. And what you see is a very nice positive correlation between frequency of use and frequency of deletion. As usage frequency goes up, you become more likely to delete also. So the important thing to see is all the words represented here are, in terms of the phonological factor we're looking at, identical. They stand before a consonant. But this variable TD deletion process is going to affect all those words, even though they are phonologically equivalent, differently based on their usage frequency. So here we have an example of a single variable phenomenon that is influenced by both grammatical and non-grammatical factors. Exactly the kind of phenomenon that I want to try and account for in the model that I'm developing. So what is the model going to look like? Since it is a constraint-based model, we need constraints, right? It's harmonic grammar, so we need the constraints that's going to evaluate the output candidates. So I'm using 4 constraints. The first one is the markedness constraint. This is the constraint that's driving the deletion process. It's just a constraint that says don't have a word that ends on a consonant cluster, the second member of which is a T or a D. So just avoid those types of utterances. Then there's 3 faithfulness constraints that will penalize deviations from the input. In this case, that will penalize deletion. There's a general don't delete constraint, a general max constraint that is violated when you delete anywhere, in anywhere of 3 contexts, before a consonant, before a vowel, or in pre-pausal context. There's 2 positional anti-deletion constraints, one that penalizes only deletion pre-vocalically and one only pre-pausally. So the important thing to see is there isn't special protection in pre-consonantal context, only in pre-vocalic and pre-pausal context. So what this means is when you delete in a pre-consonantal context, you only violate general max. But if you delete in pre-vocalic context, you violate general max and max in pre-vocalic context, right? So deletion is going to be worse pre-vocalically and pre-pausally than pre-consonantally, capturing the fact that we see most deletion in pre-consonantal context. So those are the constraints. Now, what we need to do to now develop a harmonic grammar model of this deletion process is to go and learn the weights that these constraints should have to produce these observed patterns of deletion in these different varieties of English. So to do that, we submit data like this, so these types of deletion rates, to a learning algorithm that has been developed for noisy harmonic grammar. And it is going to learn a set of weights for the constraints that will produce these particular output patterns. And it's a very well behaved, very well understood, very well studied learning algorithm. It is remarkably robust, very good at learning weights for a wide variety of variable phenomena. So if we submit these inputs, so the observed deletion rates in the different varieties of English, to the learning algorithm, and ask it to learn weights that will generate these outputs. Here you have the weights here that will learn for 1, 2, 3, 4 of these different varieties. And then on that side, you see what is the observed deletion rates in this particular variety. So this was the input to the learning algorithm. And then the expected deletion rate. So this is what this grammar would generate given the weights that it has learned when it cycled through the learning algorithm. So if you look at that, what you should see is for all 4 of these varieties, the match between observed and expected deletion rates is very good, right? And this is just 4 varieties. Any one of those varieties we've looked at, if you submit the input to the learning algorithm, you'll get a similarly close match between observed and expected rates of deletion. So this makes it look as if actually the models perform very well, right? We get very close match between observed and expected deletion rates. But this is only grammatical, right? So these models only contain grammatical constraints. It's going to treat every word the same in pre-consonantal context, irrespective of the frequency of that word. So if we look at our Columbus, Ohio example, this is how the model actually performs. So it's the same 3 panels you saw earlier, and the red dotted line is now the deletion rate predicted by this grammar-only model that we've learned. So It does well to capture the gross patterns of the grammar, but it doesn't do well in terms of individual words. It does reasonably well for high-frequency words, which is not surprising because high-frequency words contribute more to the data that made the input to the system, because high-frequency words are just observed more, so they contribute more to the data. It doesn't do very well for words that are used infrequently. It highly overpredicts deletion for them. So the model doesn't actually do as well as one would think if you just looked at, sorry, if you only looked at these. So how do we fix the problem? Here's the intuition. When we are dealing with a low frequency word, deletion rate is relatively low also. That means that the importance of faithfulness constraints are higher for low frequency words. Faithfulness constraints must contribute more to the evaluation or to the harmony score for low frequency words. High frequency words have high deletion rates, meaning it's perfectly fine to be unfaithful. So faithfulness constraints are less important. They have to contribute less to calculating the harmony score of high frequency words. And this then makes it relatively straightforward for how are we going to work this into our system. We know there's the scaling factor in the faithfulness constraints, right? So this is the faithfulness constraint part of the formula. So what we're going to do is we're just going to scale the weights of all faithfulness constraints up when we evaluate infrequent words, meaning now faithfulness constraint will contribute more to the harmony score of infrequent words. So faithfulness will be more likely because being unfaithful is penalized more heavily. And for frequent words, we scale all the weights of the faithfulness constraints down so they contribute less to the harmony score of the words. And therefore, unfaithfulness will be more likely. So we, of course, also need some kind of linking function to now map between the actual frequency of usage of a word and exactly what the frequency scaling factor for that word should be. There's many different ways in which one could do that. In the model that I'm showing here, we just did an iterative best fit procedure, so kind of searched for and found the best map between observed usage frequency of a word and scaling factor that gave us best fit with the data. So this is how the scaled model performs. The red line you already know is the line when we only relied on grammar. The blue line is now how the model performs if we allow faithfulness constraints to be scaled up or down. So just looking at it, it's obvious that it fits the data much better. It shouldn't come as a surprise because we know that frequency contributes usage frequency, and now we've given the model the ability to take into account usage frequency. And therefore it's not surprising that it does fit the data better. We can calculate the improvement in fit, so that's just a kind of rough estimate of how much the scaled model performs better in terms of mean square error, right? So it's not quite a significant improvement in fit. So what we have seen now then is a first idea of what might be happening inside of the black box. Right? So we saw how we can have a model that takes into account the grammatical context, so whether you stand in each of these three phonologically defined contexts, but also allowing usage frequency to contribute to determining exactly what commands are we going to send to the motor cortex to make the speech organs move, to pronounce that final T or not. So let's move on to the next example of such a variable phenomenon and see how well the model does if we deal with a different kind of phenomenon. And this time we're going to look at the interaction of speech rate with grammar. So how we might use our grammar differently based on the rate at which we are speaking. And we're going to look this time at it from the perspective of the listener rather than the speaker. And for this, we're going to focus on variable crossword nasal place assimilation in English. So this is the phenomenon by which a phrase like green box can be grammatically pronounced as green box with an alveolar nasal or green box with an assimilated nasal across that word boundary. So you can either say green box or green box. They're both grammatical pronunciations of that phrase in English. If you think about this from the perspective of the listener might be presented with either of these two inputs, and for perception to be successful, the listener must map both of those onto a single grammatical underlying form because they're both utterances of the same phrase. So what are the things that determines that mapping? The two that we will look at here is grammar and speech rate. So for grammar, it's going to be place of articulation. So we know from the literature that has studied this phenomenon over the past several decades that assimilation is more likely in a pre-velar context, like say green card, than a pre-labial context like green box. And place of articulation is a typical grammatical factor that we often see in phonological rules. So that will be the grammatical factor. Speech rate will be the non-grammatical factor here. Again, we know from the literature that this assimilation process is more likely to happen at faster than slower speech rates. So we're going to look at this from the perspective of the listener, so kind of just the top part of the box there. Okay, so for this, I did a perception experiment. For the experiment, I selected 10 English words that end underlyingly on alveolar nasals, right? So words like aspirin, bargain, ben, billion, cannon, and so on. And each one of these 10 words were placed in three contexts: in a pre-alveolar context, a pre-labial context, and a pre-velar context. And then they were read by a native speaker of American English, and in the pre-labial and pre-velar context, they were read with appropriate phrase assimilation, right? So something like Ben would have been read as Ben Thomas with an alveolar nasal, Ben Kingsley with a velar nasal, and Ben Potter with a labial nasal. And each of these were then synthesized at 3 different speech rates. So the slow kind of original lab speech, and then faster and fastest. The faster rate was 80% of the original recording, and the fastest 80% of the original duration and 60% of the original. So nearly twice as fast as the original one. And these 2-word phrases were then played to listeners in the experiment, and their task was to say, did you hear the alveolar final word? So in something like Ben Kingsley, did you hear an utterance of Ben? And if perception is going to reflect the patterns we know are observed in production, we would expect more yes responses in velar than labial context. So if listeners know that speakers are more likely to assimilate in velar than labial context, they should be more willing to accept a velar nasal in a pre-velar context as an utterance, an unfaithful utterance of an alveolar nasal. Similarly, if perception is going to reflect production, we should expect more yes responses at faster than slower speech rates if speakers turned listeners know that they are more likely to assimilate at faster than slower speech rates. So this is what the stimuli sound like. So this is the slow original recording of Ben Kingsley.
Ben Kingsley.
It's not very loud.
Ben Kingsley. Ben Kingsley.
And faster.
Ben Kingsley. Ben Kingsley.
And then fast.
Ben Kingsley. Ben Kingsley. Ben Kingsley.
So the question is, do you get more Ben percepts as speed increases? And the same for the labial cases. Slow.
Ben higher. Ben higher.
Faster.
Ben higher. Ben higher.
Fast.
Ben higher. Ben higher.
So do you get more as the speed increases? Maybe the volume isn't high enough. Anyway, this is what the result looked like. So first we see the nice clear difference between the 2 grammatically defined contexts. There were more yes responses in velar context like Ben Kingsley than in labial context like Ben Potter. So we see the reflection of grammar, as we also know from the production literature. There's also a very nice speech rate effect, so more yes responses at faster and less at slower speech rates. So again, exactly the type of phenomenon that I'm after, one where we see a clear contribution of both the grammatical context, place of articulation, and a non-grammatical context, here, speech rate. So now we need to again just build the model that's going to generate these patterns. And by now you should know how I'm going to do that. Since it's a constraint-based model, first we need a set of constraints. There will be the markedness constraint, agree place, that just says a nasal must agree in place with a following consonant. So this is the constraint that's going to be driving the unfaithful mapping of place. And then a set of faithfulness constraints. There's 3 faithfulness constraints. One that says max coronal, so don't delete a coronal place. Whenever you assimilate a coronal nasal to another place of articulation, you lose its coronal feature. So it will violate this constraint that says don't delete the coronal feature. And then 2 constraints against acquiring labial or dorsal feature. So if you go from a coronal to a labial, you lose your coronal feature and you gain a labial feature. Right? So you violate those 2 constraints. So those are the constraints. Now we need to learn the weights for the constraints that's going to generate this type of pattern. And I'm going to do it the same way I did for TD deletion. We first abstract away from the non-grammatical factor, which here is speech rate. So let's go and calculate the average percent yes responses in labial and velar contexts, ignoring the differences between the different speech rates. And lo and learn a weight for the set of constraints that will generate that average pattern of deletion. So if we do that, this is how the model performs. The broken line shows what the model is now going to do. So it clearly captures the effect of grammar, the difference between velar and labial, but obviously it doesn't capture the non-grammatical input year speech rate because we averaged out between the different speech rates. So now we just need to scale the model to allow for speech rates to contribute, and you already also know how to do that because it's exactly the same principle as for usage frequency. Slower speech rate shows less assimilation, so more faithfulness, so the faithfulness constraints have to be scaled higher, they're more important. Faster speech rates show more deletion, so faithfulness constraints are less important, they have to be scaled down. So exactly the same, we have the now invisible, the rate scaling factor there, which is going to just scale faithfulness constraints up or down depending on the speech rate that the listener is exposed to. So once we allow that into the system, this is how the performance are. So the broken line is the system where we didn't allow speech rate to contribute. The solid yellow line is now allowing speech rate, and the green line is the observed data. The solid blue line you can't even see because it's completely covered by the green line, which is the observed data. So once we allow speech rates to contribute, obviously the model is going to fit the data much better. And this time if we use mean square error to determine the improvement, you know, it's a 95% improvement over the model that did not allow for speech rate to contribute. Again, not surprising because we know speech rate contributes, and we've now given the model the ability to incorporate speech rate. Okay, so we've now seen two examples of what happens inside the speech box, the black box. Grammar interacting with frequency and with speech rate. I'll work through one more example, and this is going to be at how grammar interacts with the role that an individual plays in the communicative interaction. So whether that individual is a speaker or a listener. So it's kind of looking at it from the perspective of both listeners and speakers this time. And here we are going to look at the production and perception of voicing in Afrikaans. So I have a whole host of collaborators on this project, and I have to also acknowledge the NSF because they funded part of this research on this phenomenon in Afrikaans. So let's think a little bit about what's the relationship between perception and production in an individual person. They have to be related because it's after all the same person who's speaking and perceiving. But they can't be absolutely equal to each other. Perception has to be more flexible than production, right? You're listening to me at the moment and I speak with an accent different than your own accent, but you should still be able to understand me. So your perceptual grammar has to be a little bit more flexible than your production grammar. You have to be able to interpret more variation perceptually than what you will ever produce as a speaker yourself. And this is especially true if we're in a speech situation, a speech community, where there's a lot of inter-speaker variation, which is what is typically what you observe in a speech community that is going through a sound change. You will have some speakers for whom the sound change is further along, and others for whom it isn't that far along. So as a listener in that community, you will be exposed to people who are far along and people at the beginning of the sound change, and you must be able to understand all of them. So the assumption I'll make is that as a member of a speech community, you use basically the same grammar whether you are speaking or listening. You're just going to use that grammar differently depending on whether you speak or listen. And the way in which you're going to use it differently is your faithfulness constraints will be moving up or down depending on whether you're a speaker or a listener. So the same way in which we've scaled the grammar for frequency and speech rate, the markedness constraints, which basically capture what is the grammatical structures in the grammar, they stay in the same place. The faithfulness constraints, how willing you are to be unfaithful, might move up or down depending on whether you are speaking or listening. So some information about Afrikaans. Afrikaans traditionally has been described and traditionally also has been a language that has real voiced plosives, so with pre-voicing during the closure of the plosive. and voiceless unaspirated plosives. So quite different from English, where you have voiceless unaspirated and voiceless aspirated plosives. Afrikaans had voiced plosives and voiceless unaspirated, right? So a voiced plosive would be something like ba, with, you know, that voicing before the plosive during the closure of the plosive. Ba and pa would be the voiced voiceless distinction in Afrikaans. So that is how it has been traditionally described, and indeed what the language had been until quite recently. What's currently happening is that this voicing contrast in the plosives are collapsing. So the pre-voicing is being lost, and the plosives are merging into one category, voiceless unaspirated. But the lexical contrast is being maintained. So the contrast between a word like bus and pas, so a voiced and voiceless one, is maintained not in the plosive, but in the vowel. So the vowel after plosives that historically were voiced now has a low tone, and the vowel after plosive that historically were voiceless now has a high tone. And this is currently ongoing in the speech community. So we have some speakers for whom this change is far along, and some for whom this change has just started. So it's exactly this kind of situation where, as a listener, you'll get varied input, but as a speaker, you might have only one specific pattern. So in the study, we looked at two groups of speakers in the community. Older people, so these are all based on women, so we don't have data from men at the moment. The older group were all over 60, and the younger group all under 25, so two quite different generations. And this shows the data for just two of the participants in our experiment. And I chose them because they're kind of two extreme examples at the two endpoints of the change. So let me orient you. Here we have the older speaker and the younger speaker. And this is the older speaker producing something like ba, so with a phonologically voiced plosive, and something like pa with a phonologically voiceless plosive. Blue bars are tokens that were produced with actual voiced plosive, so actual voicing during the closure of the plosive, and yellow bars all correspond to voiceless unaspirated productions. So if you look at the older speaker, things that were phonologically voiced were predominantly produced with voicing during the closure, and voiceless ones were predominantly produced as unaspirated. If we look at the younger speaker, there's virtually no blue bar, so the younger speaker is producing virtually everything as voiceless unaspirated. Now, in addition to this contrast between aspiration and voicing, there's also an F0 or a tonal contrast. So here we have, for this speaker, divided the speaker's F0 range, or kind of pitch range, into three regions. The lowest third, the middle third, and the high third, roughly corresponding to low, mid, and high tones. So we see for the older speaker, phonologically voiced tokens are not only produced with voicing during closure, but also with low tone on the vowel. There's nothing here in the high category. Voiceless ones are not only voiceless, but also have higher tone. So the old speaker cued this contrast both in terms of voicing on the consonant and tone on the vowel. The younger speaker, which has collapsed the consonant contrast, has maintained the tone contrast. So the phonologically, historically voiced ones have low tone vowels. The voiceless ones have nothing in the low category, primarily mid and high tone. So the young speakers maintain the contrast, but on the following vowel, not on the plosive consonant. So this is the production patterns. The same participants also did a perception study, participated in a perception study. And here are the results for these two individuals in the perception study. So in the perception study, we crossed these two possible cues for voicing. So we had some tokens that had voicing during the closure, and some that lacked voicing during the closure, some that were voiceless unaspirated. And then each one of them were paired with vowels that had a low tone, a mid tone, and a high tone, right? So you had something that had voicing during the closure with high, mid, and low tone, something without voicing with high, mid, and low tone. And our listeners were exposed to these, and what they had to do was say, did I hear ba or pa? Did I hear the voiced or the voiceless token? So what's being plotted here is the percent times that each of these listeners said they heard the voiced token, so the ba token. So the blue line represents tokens where there was voicing during the closure itself. The plosive itself was voiced, and a low tone on the vowel, a mid tone on the vowel, a high tone on the vowel. So the older listener heard it as voiced, as long as there was voicing during the closure, it didn't matter what the tone on the vowel was. The older listener relied on voicing during closure to decide. When there wasn't voicing during the closure, so voiceless unaspirated, then our older listener used the tone, right? So even though there isn't voicing on this vowel, since it's a low tone, it was identified as a voice category, which is kind of good that she performed like this because, you know, this is when she were to listen to this one. If she has to understand her grandchildren, she better be able to interpret a voiceless consonant with a low tone vowel as a production of the voiced category. The young listener looks quite different, right? If you look at the blue line, so this is now, there was voicing during the closure, and the vowel was low-toned, mid-toned, or high-toned. Voicing is completely ignored. The younger listener relies only on the tone on the following vowel. So the young listener also perceptually has shifted her cue weighting and just ignores the voicing during the closure of the consonant, just using a pure tonal system. So what's the relationship between the production and perception patterns that we see here? In general, what we see is that faithfulness is less important when doing perception than when doing production. And we see it at two different places for the older and the younger participants in the study. So this is something that was phonetically voiceless. It was a voiceless plosive, but at a low tone. And our older listener was willing to accept that as a production of the phonological voiced category, so an unfaithful production, saying it was underlyingly voiced, it was produced as voiceless, but I'm still going to accept it as a production of the voiced category. So that's an unfaithful production. The older listener doesn't produce tokens like this. This would have been this yellow bar. So very few productions like this, so more faithfulness in production, but many quite willing to accept these in perception, so less faithfulness in perception. We see the same general trend of less importance of faithfulness for the younger speaker, but in a different place in the system. So this blue line is a token that was produced phonetically as voiced. So it was actually voiced. But this listener is happy to accept that as a production of the voiceless category. So again, an unfaithful mapping, phonologically voiceless, phonetically voiced. And this would have been if there were voice productions here, right? So we don't see it in her production patterns, but we see it in her perception patterns. So generally, the pattern that arises is faithfulness is less important when doing perception than when doing production, which shouldn't be surprising because as a listener, you're going to be exposed to people who speak differently than you. So you have to be willing to accept more deviation from your own way of speaking. So now we need to build a model for this. And again, because we're doing harmonic grammar, we need constraints. So quickly, the constraints that we're using is a general faithfulness constraint that says don't change voicing. So this will be violated whenever you produce a voiced, underlyingly voiced consonant as a voiceless or an underlyingly voiceless one as voiced. And then we have a set of markedness constraints. Don't have a voiced obstruent, which will be the one that's driving the devoicing process. Just like, let's get rid of all voiced obstruents like the plosive but. And then a series of constraints that regulate the relationship between the voicing of the initial consonant and the tone on the following vowel. So there's one that says, don't have a voiced consonant with a low tone, a voiced consonant with a mid tone, a voiced consonant with a high tone, and similarly, a voiceless consonant with each one of the three tones. Okay, so now we have the constraints. We need to go and learn the weights associated with these constraints to produce patterns like this. So what we did in this instance is to learn two separate grammars, one for the production grammar and one for the perception data. So two separate grammars for the young speaker and two separate grammars for the older speaker. And when we did that, what we found was that the weights of the markedness constraints, everything from here up to the top, was virtually identical between production and perception. There was very little difference in the weights for the markedness constraints between production and perception. The weight for the faithfulness constraint was drastically different for both participants between production and perception. So the average weight of the faithfulness constraint, so that's ident voice at the bottom, for the older listener, average between the two grammars, perception and production, was 53.6. But that was nearly 49 units higher in production, where faithfulness is more important, and 49 units lower in perception, where faithfulness was less important. For the younger speaker, the average weight was like 48, and it was actually exactly the same spread, 48.8 units higher in production and lower in perception. I don't think there's something magical about 48.8. I think that's accidental that it was the same for the older and younger speaker. What is not accidental is that for both of them, it was higher in production and lower in perception, whereas for both of them, the weights of the markedness constraints was virtually identical between the perception and production grammars. So now we can use the weights that we've learned here and stick them into our formula, which by now you should be familiar with. So this is where the perception production scaling factor is going to come in, which will be this 48.8. So we scale the weight of faithfulness constraints up by 48.8 when doing production and down by that much when doing perception. And if we then run this model to predict observed patterns of variation, this is how the model performs in comparison to the observed data. So the solid bars is the observed data, and the kind of fuzzy bars, the predicted patterns given this model. So you see a relatively close match, mostly voiced productions, mostly low tone, mostly voiceless productions, mostly higher tones. And the same here, mostly voiceless productions, but mostly at the low end point, mostly voiceless, but mostly at the high end point. And also a similar decent match in the perception data. Not as close, but we see at least the gross patterns that we observe in the perception data are matched by this scaled model. So we've now used the same grammar, but use it differently depending on whether we are a speaker or a listener by just moving the faithfulness constraints. So we've slowly started to fill in these fans that point into the black box. Slowly started to develop a model for what might be happening inside of the black box. Now in the black box we put together the contribution of grammar and these non-grammatical factors that all co-determine what goes out the mouth of the speaker or how a listener interprets what comes in through his or her ear. And this is the model of the black box that I've been working with today. Right? So at the top we have kind of unscaled noisy harmonic grammar. That's a purely grammatical model. There's no place for the non-grammatical factors in there. The model for the black box that I have been working here is the one below, where we split the constraints between the faithfulness and the markedness set, and this is where the non-grammatical factors come in. They are these scaling factors that's going to move faithfulness constraints up or down depending on what context the language is being used in. Frequent words, infrequent words, different speech rates, speakers, listeners. It's just going to move the faithfulness constraints up or down. So this is the specific proposal for what happens inside of the black box. It works well for these three examples of data that I've looked at. I don't know if it will work well for any set of data. So this is, I think, an open empirical question. There's now a specific proposal for what might happen inside of the black box. It's going to make predictions about the types of variable patterns that we should observe and not observe. Now we need to go out and collect the data that specifically look for interactions between grammar and non-grammatical factors to see how well this model translates and accounts also for more examples of this kind. My suspicion is it's not going to do as well as it did for these three. I selected them because they work well for these three, right? So we need to go and figure out where it does work, where it doesn't work, and then adjust and fix it as needed, based on the data that we find. So in the last 4 or 5 minutes or quicker, want to run very quickly through some of the predictions that this particular model makes so that we know what the kinds of things are where it could be falsified. One thing that it does is that this is a grammar dominant model. So we're now back at where we started, saying grammar sets the limits of possible variation, and the non-grammatical factors can't move us outside of that grammar defined space. A very easy example in which we can see that is in the TD deletion case. So you'll remember that deletion was always most common preconsonantally more so than pre-vocalically or pre-pausally. And that was hard-coded into the grammatical model by the constraints that we selected. So there was a general max constraint that's violated by deletion in any context, so that's the only faithfulness constraint violated by pre-consonantal deletion. And then in addition to that, there's two positional constraints that's violated either in pre-vocalic or pre-pausal context. So what that means is a deletion candidate in pre-consonantal context violates only general max. So its harmony score is going to depend only on the penalty that general max assigned to it. Deletion in pre-vocalic or pre-pausal context violates general max plus one of the two special contexts. So their harmony scores depend on the penalty that they get from general max and the special faithfulness constraint. So no matter what the specific weights are of these three faithfulness constraints, no matter how we scale them by non-grammatical factors, that mathematical relationship between their harmony scores will always hold. Harmony score of a pre-consonantal deletion candidate will always be higher than the harmony score of a pre-vocalic or pre-pausal context. So deletion pre-consonantally will always be less bad because it's penalized by fewer constraints. And that's not influenced by scaling the factors. So grammar tells us always most deletion pre-consonantally, and none of this weight scaling factor can overthrow that grammar specified property of the variable system. So in this sense, it's a grammar dominant model. Is that true, or can we find examples of variable phenomena when non-grammatical factors overpower or trump grammar? If we can, then this grammar dominance part of the model is not right, and we need to fix that and give the non-grammatical factors more power. I'll talk about only one more thing and then I'll end, and that is the question of how these non-grammatical factors are related to each other. Are they independent from each other, or can they interact? The way that I've implemented them here, they're independent, right? So the weight scaling is additive. I just scale the faithfulness constraints up or down, and if I throw in both frequency and speech rate, those two things will just add up and move the weight of faithfulness constraints by the sum of those two rate scaling factors. If these non-grammatical factors interact with each other, then that's too simple a model. Then we'll need some kind of meta model that sits outside of this that says, let's take all the non-grammatical factors, stick them into some thing that will now weight them relative to each other and create one scaling factor which now feeds into the system. The reason that I've implemented them here as independent from each other is for instance, it's not very clear in this dark blue background, but for instance, in the nasal assimilation study, statistically speaking, there was no evidence for an interaction between place of articulation and speech rate. So as speech rate goes up, statistically speaking, the rate of assimilation didn't differ between, the size of the difference between labial and velar context remained the same. But if you look at the lines, as the rate becomes lower, they start separating. Right? So I don't know if we had an even slower speech rate, if they would have separated sufficiently that there would have been a statistical difference between them. Right? So it is conceivable that, say, the grammar and these non-grammatical factors might interact, and then this just additive incorporation of the non-grammatical factors might not work. It's also conceivable that, say, speech rate and lexical frequency, usage frequency might interact with each other. It might be the case that, say, an extremely frequent word is going to have a high deletion rate irrespective of the speech rate, but a very low frequency word might be more influenced by speech rate. So if they interact with each other, we'll have to somehow complicate the model so that it's not just an additive system. So this is a proposal for what might be happening inside of the black box. It works relatively well for these three data sets I've looked at in most detail. I don't think it's the final model, but I think it at least gives us a concrete place at which to start to now go and design the studies we need to figure out how to fine-tune this model. Thank you.